So next question in the Bluebook test preview for Calc BC says we've got a curve defined by parametric equations x of t and y of t. Which of the following expressions represents the second derivative of y with respect to x in terms of t? Now, first task here is to find the first derivative of y with respect to x. We can't find the second derivative unless we have the first. So there is a calculation you've done to find slopes of tangent lines to parametric curves. We're going to take the rate of change of y with respect to t divided by the rate of change of x with respect to t in order to find the rate of change of y with respect to x. So if I do the derivative of y, I am in need of using a chain rule, so that's what you see in this numerator. And then the derivative of x of t is a little nicer. I'm going to get 2t. And what's really nice here is those 2t's, because there's no addition or subtraction present in the top or bottom of this fraction, those 2t's are going to be able to cancel with each other. And so this dy dx, the first derivative of y with respect to x, simplifies to cosine of t squared. Now, the way that I would get the second derivative of y with respect to x is I would do the derivative with respect to x of dy dx. Now, the issue that we have is that dy dx is not dependent on x right now. It's dependent on t. So what I'm going to have to do is I'm going to have to use implicit differentiation. I'm going to have to take the derivative of y with respect to x with respect to t, if that makes sense. So I'm taking the derivative of dy dx with respect to t, but then to finish my implicit chain rule, I'm going to have to multiply by the derivative of t with respect to x. Now, that's not that easy to determine, so what's a lot more convenient when you're finding second derivatives implicitly is Leibniz notation. Essentially follows the laws of algebra. Rather than multiplying by dt dx, we can divide by dx dt. So if I take the derivative of dy dx, which is right here, with respect to t, I do a chain rule. So I'm going to get negative sine of the inner function times the derivative of the inner function. Derivative of dx dt is the same derivative we had down here, 2t. Once again, we get some nice cancellation to occur, and our second derivative of y with respect to x is negative sine of t squared.